One of the topics that we just finished up was energy, and we're coming back to it now within a rotational context. So imagine we have some sort of object that is rotating through an axle, and we can think about the fact that every single individual point of it, having its own mass, has a velocity. So we could talk about this as having a kinetic energy even if the whole object isn't flying through the air. So this is a case where we're saying the translational motion is zero, the axle is staying fixed, but it's rotating. So how do we talk about the energy of that? So we're going to start with our old-fashioned kinetic energy equation, where we say we have all of these individual points and each one has a different velocity. Why do they have a different velocity? Because they're at different radii. However, our entire object must be turning as one object. That means we can take these individual velocities and relate them to the angular speed of our object and the distance they are from our axle or our axis. So all we've done is replaced the linear velocity with the radius it's at and the angular velocity, remembering to square it. Well, now every single one of these has the same angular speed, and every single one of these is going to have a 1/2. However, there's a sum in between of the mass and the distance that piece of mass is from the axis squared, and maybe by now you will recognize that this is actually moment of inertia. So when we have an object that is rotating, it has kinetic energy due to every piece of it moving, and we can write that as 1/2 I, where I is moment of inertia, omega squared. And the book goes through this derivation. I think it's helpful to see that this isn't really new. It's the same idea as kinetic energy earlier, but now we have to consider the whole size and shape of the object rather than just taking it down to a point. If we pulled this into a point, it wouldn't look like the point was moving at all. So let's do some equation converting. Again, we can take what we used to know in linear motion and we can convert it into a rotational equation. We've said that mass is going to be moment of inertia for any rotational situation. So instead of m, I have I. And what is familiar, hopefully already, is that instead of having linear speed, or the magnitude of velocity, you have rotational speed, or angular speed, omega. So instead of having 1/2 mv squared, you have 1/2 I omega squared. So we did the derivation on the last slide that shows that this will be true. However, you can also kind of take your old equations and convert it. These new rotational equations are on the equation sheet, but it's also just helpful to get a feeling for it. So let's return to our basic energy model and actually think now about what mechanical energy means, because now that we deal with rotation, we have to think about it slightly differently. We have rotation around a fixed axis. This may or may not be the center of mass. Later, when we talk about rolling motion, it will be, but right now it's not going to be. So I omega squared times 1/2 what we just said. Now, if you have combination motion, where there's both translation and rotation, you still need your old kinetic energy. This kinetic energy is for pure rotation. It doesn't include any translational motion. So for this, you have to think about the translation of the axis point where it's rotating around and or the center of mass. And normally for this, we think for combination motion, we're talking about center of mass being the point that it rotates around. And so one way of denoting this is K underscore CM for center of mass. And again, this is translational motion, and then it's 1/2 mv, which you know, and this is again the velocity that the point around which the object rotates is moving. So again, if you imagine an object like a hammer that you've thrown through space, like you've just tossed the hammer across the room, the hammer is spinning around itself, but then the center of the hammer, the center of mass, is also moving with a linear motion, and that's what goes in here. And when I say linear motion, it's linear motion in 2 dimensions, that's fine. So then, we need to return to gravitational potential energy. And before, when we had a point particle, you just said, okay, well, where's my point at? But now we have an extended object. And for this, the potential energy is going to be the y, the height, of your center of mass. And so this is important to think about. It's still the total mass of the object. So capital, these M's are theoretically the same. Sorry about that. But what's important here is that it's not the height of the highest point or the lowest point of the object, it's the height of the center of mass. So what does that look like? If we have an isolated system, which is non-dispersive, isolated system means no external forces, which means no external work. Non-dissipative means no change in thermal energy. We then know that energy is conserved, which means the change in rotational kinetic energy plus the rotation in translational kinetic energy plus the change in our potential energy, where now we're thinking about the center of mass, gravity, is zero. So this is your conservation of energy equation, assuming your system is isolated and non-dissipative for the rotational case, because now we have two types of kinetic energy corresponding to rotational and translational motion, and then we think about a gravitational potential. So we might be able to simplify this down based on the problem. So here's an example from the book. We have a rod which is on a hinge at the corner. It's initially horizontal and then it's dropped down. The specific problem in the book asks to find the velocity of its tip when it hits the wall. But let's just talk about how one sets this up as a conservation of energy problem. So first, you should recognize that this is an energy problem because you're not concerned with time. There's a before situation and then there's an after situation. So that's what you would draw, a before and after representation, and we would think that initially we're going to have zero rotational speed. But at the end, there is some rotational speed. And the other thing you need to track here for potential energy is the position of the center of mass. You can define y equals 0 to be wherever you want. In this problem, y equals 0 was defined to actually be the initial height. So our initial center of mass height is 0. The final center of mass height is negative 1/2 L, because for a rod, we know center of mass is 1/2 L. So initially, you have gravitational potential energy. This is being transformed into rotational kinetic energy. So it's at some height, it can go down, but it's actually rotating down. So we wouldn't call this translational motion because it's rotating around a fixed point, even though that point isn't at the center of mass. So the height that we need for calculating gravitational potential energy is the height of the center of mass. It's not the height of the end. You'll get the wrong answer if you use that. You must use the height only of the center of mass. And then make sure that you've identified the axis of rotation. In this case, it's telling you that there's a hinge there, which tells you that that is the axis of rotation. If you treat it as a different point, that's incorrect. So later for other problems, you might have to think about that in more detail. This one's pretty simple. When you draw your representation, if there is rotational motion, you want to clearly denote where your rotational point is. And in general, you should use that point as the origin of your coordinate system. If you have a fixed point of rotation, have that be your origin. The last thing to remember is that because we're transforming gravitational energy into rotational kinetic energy, we need to use the moment of inertia of the rod, right? It's rotating, it's not just translating, and the rotation is then going to be I, and you can look that up in the table to know what it is from a rod.